Good morning. I welcome you all to this session of fluid mechanics. The last class we started the discussion on flow meters, and if you recall, we discussed that there are three types of flow meters, namely venturi meter, orifice meter and flow nozzles, which work on the same basic principle. Flow meter means if you want to measure the flow rate of a fluid flowing through a fluid circuit. To measure the flow rate, these three flow meters, venturi meter, orifice meter and flow nozzle, they work on the same basic principle that these meters provide a geometrical change to the flow of fluid, usually a coaxial contraction to the path of the fluid flow, so that a pressure drop is registered in the flow of fluid between two sections, and at those two sections the pressure drop is measured by a pressure measuring instrument, which is usually a manometer, and then by the straightforward application of Bernoulli's equation we derive a equation and mathematical expression relating the flow rate and the pressure drop, and flow rate is found out. So let us discuss one by one these flow meters as the applications of fluid flow. So let us discuss first the venturi meter. Venturi meter. Venturi meter. This name of the venturi meter comes from the name of an Italian scientist, Venturi. Venturi is the name of the scientist. So a venturi meter looks like this. It looks like this. If you draw a venturi meter, it will look like this. It is like this. That means a venturi meter consists of a convergent and a divergent. A convergent, that means two conical parts. Rather, it is better to tell two conical parts connected with a straight portion. Now, the characteristic feature is that one conical part is of shorter length. That means this one is of shorter length. This one is of shorter length, this part. Whereas another conical part is of higher length. That means this cone angle is high, whereas this cone angle is low, of higher length. Usually this venturi meter is installed in the fluid flow path in this way that the flow direction is like this. This is the direction of flow. That means the shorter length part, higher convergence angle, is a convergent duct. Higher cone angle conical part, it becomes a convergent duct. That means when fluid flows, this acts as a convergent duct. Whereas the longer length part, that is the conical part with a lower cone angle, acts as a divergent duct. Why it is made? It is very important. Sometimes it is asked in many interviews that if you are given a venturi meter, two conical parts, which way you will place? You will place in such a way that the fluid flow direction is such that it first goes to the shorter length, that is the higher cone angle conical part, and then lower cone angle conical part, or the vice versa. It is done like that. This is because in this case, when the flow takes place through a convergent duct, whether the angle of convergence is high or low, it is an accelerating flow. Why? The velocity increases, the area decreases in the direction of flow. So therefore, from the continuity, the velocity increases. That means this is an accelerating flow. As a consequence of Bernoulli's equation, pressure decreases. So therefore, always pressure at the upstream is higher than the downstream, which means the fluid is flowing with a favorable pressure gradient. That means the pressure force to any fluid element is always in the direction of the flow. In this case, the separation loss, as we discussed earlier, doesn't take place. That means the fluid particle near to the wall cannot flow back. Whereas in the divergent duct, when the fluid flow takes place, you see from the continuity, since the area increases, what happens? The velocity decreases, and hence the pressure increases. So therefore, in the direction of flow, there is an increase in pressure, which means the fluid is flowing against an adverse pressure gradient, which means that in a fluid element, the pressure forces is always in the direction opposite to the flow, but still the fluid flows because of the energy gradient. So in this case, the fluid particles very near to the wall, which loses their kinetic energy, because of the friction, fluid friction, then cannot overcome this adverse pressure hill, and they flow back with the favorable pressure forces. That means the pressure forces in this direction. That is the separation loss we discussed yesterday. So therefore, this separation loss is avoided or it is minimized if the angle of divergence in the divergent part of the flow is made very less. Usually in all design, the divergence angle is made between 8 to 10 degrees. So therefore you can make a very high convergence angle, but we cannot make a very high divergence angle. Whenever there is a divergent duct in a hydraulic circuit or a fluid circuit, the angle of divergence should be limited to 8 to 10 degree. You understand? 8 to 10 degree, so that the separation loss is minimized. This is the reason for which the upstream part corresponds to the rapid higher cone angle or a shorter length, and the downstream part corresponds to a lower cone angle, higher length. Now what happens? Throat is this section is known as throat. Throat, T-H-R-O-A-T, throat. This is upstream. This is downstream section. This is throat, T-H-R-O-A-T, throat. Throat is the minimum section. Minimum section means, minimum area, minimum cross section, minimum area section. Now as the fluid flows through this in this direction, the maximum velocity occurs at the throat. That is the minimum area part. It is a very short straight portion which connects these two conical parts. Similarly, the pressure here is the minimum, velocity here is the maximum. According to continuity, pressure here is the minimum. So if we measure the delta P between these two, there is a pressure difference between these two sections. Let this section is 1, let throat section is 2. P1 is greater than P2. We measure the pressure difference and find out the flow rate. How to do it? Let us consider a practical installation. Now let us consider this venturimeter is installed in a pipeline where the fluid is flowing. Venturimeter as an instrument is installed with the flange. It is connected in the pipeline. This is a practical thing. Now let us consider the pipe is inclined in a vertical plane, in a general. Let us consider the most general case. Let this be the pipe. This is the pipe. Let this be the pipe. Let this be the pipe. And this part is the venturimeter, which is inclined to the, installed in the pipe. Pipe is inclined in a vertical plane. Now therefore, this is the section 1 of the venturimeter, upstream where the fluid flow is uniform, then it comes to the convergent duct. This is the direction of the flow, then it attains a minimum velocity. This is the throat, let this be the axis, okay, and this is the downstream part. So venturimeter is installed in the pipeline, which is an inclined pipeline transporting water in this direction in a vertical plane. Alright, now what happens if this section is denoted as 1 and if this section is denoted as 2, then we can write from the Bernoulli's equation between these two sections, let the pressure is P1, velocity is V1, the throat section, let the pressure is P2 and the velocity is V2. And if we consider the Z2 as the elevation head and here Z1 as the elevation head from any reference datum, then I can write the Bernoulli's equation P1 by rho, okay, plus V1 square by 2, okay, rather P1 by rho g, you write in terms of the head, plus Z1. Considering the inviscid fluid, I can write P2 by rho g plus V2 square by 2g plus Z2 without any loss. That means considering the fluid to be inviscid, Bernoulli's equation between these 2 points, 1 and 2. Then what we can write? Now after this, what we can write, V1 and V2 may be connected through the continuity equation. Let us write that V1 A1 is equal to V2 A2. We can write the continuity equation where area is A1, that is the area of the pipe, which matches this base diameter of the venturimeter, the same area here A1. But the throat area of the venturimeter is A2. It's very simple, V1 A1 is V2 A2. It is from the continuity. Under steady state, the same flow rate passes through all sections. Then if I just eliminate V2, then what we will get? V2 is V1 A1 by A2. That means we can write V1 is V2 A2 by A1. So therefore we can write V2 square by 2g, V2 square by 2g, we take here 1 minus, what is V1 A2 square by A1 square, that is V1, is equal to P1 by rho g plus Z1, let this minus P2 by rho g plus Z2. Let us define this P1 by plus Z1 as H1 star, and this is defined as H2 star. So we can write V2 square is H1 star minus H2 star. This is H1 star, this is H2 star. 2G, of course, 2G into 1 minus A2 square by A1 square. Alright, or we can write V2 is equal to root over 2G H1 star minus H2 star divided by root over 1 minus A2 square by A1 square. This is very simple. Now, this is very simple algebraic steps, but this H1 star and H2 star represents the pressure head plus the datum head at the inlet, and this is the pressure head plus the datum head. This as a whole is known as piezometric pressure head. Piezometric pressure, we have already discussed what is piezometric pressure. That takes care of both the pressure plus the corresponding equivalent pressure due to a static pressure due to the height of the liquid. That means in terms of head, it is the pressure head, pressure energy per unit weight plus the datum head. That means due to the height of the liquid from any arbitrary datum. So combination of P1 by rho g plus Z1 is the piezometric pressure head. So we can write in terms of piezometric pressure head. Why we write in terms of this? There is a meaning to it. Mathematically here it may not be very meaningful that why unnecessarily we are writing H1. Let us better recognize P1 by rho g, P2 by rho g separately with Z1, Z2, the elevation at 1 and 2. No, it should be written in terms of this. This is because in fact what is done, we attach a manometer between these 2 points to register the pressure difference. Now let us consider any manometric liquid. Since P1 is greater than P2, so therefore the manometric liquid will take a position like that, where this is the deflection delta H. Now if I write the manometric equation and consider the manometric fluid density as rho m, consider the manometric fluid density as rho m, alright, consider this as rho m, then we can write the manometric equation considering here the pressure P1. Now we write again, if we recall the hydrostatics, that P1 plus here the rho is the density of the working fluid, that is fluid flowing through the pipe, and the venturimeter, G into Z1. Let we consider this level as the level 0, 0, where, or O, 0, 0, where we are finding out the pressure from both the sides and equating it. And let the elevation is Z0. It is easy if we just define the elevations like that from a reference datum to find out the height. That means this height is Z1 minus Z0. So this is the pressure from this side. What is the pressure from this side? Is equal to P2 plus rho g Z2 minus Z0 minus delta H. Okay, Z2 minus the elevation head minus Z0 elevation head. This one minus delta H, minus delta H. So this is the pressure head due to this plus this one plus rho m g delta H. Well, if you now write it, it will be like this: P1 minus P2 is equal to, so rho g Z0 and rho g Z0 will be cancelled. So rather not P1 minus P2. I am very sorry, my entire objective is different. So it will be P1 plus rho g Z1. I am sorry. So it will be now P1 plus rho g Z1. So rho g Z0 cancels. Minus P2 plus rho g Z2 is equal to this, and here also rho g delta H, that means rho m. This already we recognized earlier, delta H. That means P1 plus rho g Z1 and P2 plus rho g Z2, these are the piezometric pressures, not the static pressure. This is the static pressure, or the pressure, this is the piezometric pressure, plus the equivalent pressure for the height Z1, Z2 measured from any arbitrary reference datum. So if you divided it by rho g in terms of head, that is P1 by rho g, plus Z1 minus P2 plus P2 by rho g, P2 plus rho g plus Z2 is equal to then rho m by rho minus 1, okay, in delta H, which means that the difference in piezometric pressure head is nothing but rho m by rho minus delta H. So now this rho m minus rho by delta H is ultimately replaced here, H1 star minus H2 star. That means if we replace this, if you just recall this equation, this becomes V2 is equal to root over 2g, again I am writing this, H1 star minus H2 star by root over 1 minus A2 square by A1 square. We write V2 is equal to root over 2g, H1 star minus H2 star is rho m by rho minus 1 into delta H, and there root over 1 minus A2 star by A2 square. Now thing is that when the venturimeter is horizontal, that means this pipe is horizontal and venturimeter is horizontal, in that case what will happen? H1 star minus H2 star is H1 minus H2, where H1 is equal to P1 by rho g and H2 is equal to P2 by rho g. That means Z1, Z2 is different. And in that case delta H into rho m by rho minus 1 will give you the value of H1 minus H2, which means that if you write the equation for V2 in terms of the deflection of the manometer, then it is immaterial whether the venturimeter is inclined or horizontal. This is a very important point. But if you write the equation in terms of P and Z1, then it is very important, because whether Z1, Z2 will be cancelled or not, it is very important. If you write here instead of H1 star H2 star P1 by rho g plus Z1 P2 by, because in that case H1 star minus H2 star is not always P1 by rho g minus P2 by rho g. If it is a horizontal, H1 star minus H2 star is H1 minus H2, then P1 by rho g minus P2 by rho g. Otherwise it will be P1 by rho g plus H1 minus P2 by rho g plus H2. You have to be very careful whether it is inclined or horizontal. But if you straightforward write the V2 formula in terms of the deflection of the mercury, then it is immaterial, because the manometric equation which we discussed earlier is such that if it is written in terms of the deflection of the manometric fluid, then this equation represents the difference of piezometric pressure between the 2 points between which the manometer ends are connected. So whether they are in the horizontal plane or is displaced vertically, it doesn't matter. Ultimately this value gives the difference in the piezometric pressure, that means difference in static pressure plus the equivalent pressure due to the elevation head. So therefore it is immaterial whether the venturimeter is horizontal or not, pipeline is horizontal or not, if you use this equation. Alright, now if I write this equation again, what we get? We get V2 is equal to root over 2g. So this is a very, very important conclusion. Sometimes it is asked even in the interviews that will you be very careful if the venturimeter installation is not perfectly horizontal? The answer will be no, because if I write the expression in terms of the mercury deflection in a manometer, if the mercury is the manometric fluid, deflection of the manometric fluid, it becomes the same the equation. So now this is the value of the V2. Now therefore the Q will be, flow rate will be V2 into A2. If you recall, the A2 is the area where the V2 was found out. That means this is the throat area A2 where the velocity is V2, so flow rate is velocity into the area. So that means A1, A2, if I simplify, then root over 2g into rho m by rho minus 1 into delta H divided by root over A1 square minus A2 square. Now see that I can find out the flow rate if I know the area of the venturimeter, that is venturimeter inlet and throat diameters are known, because it is known from the geometry of the venturimeter. And if I know the deflection of the manometer. That means if a manometer is connected between 2 points, so the measuring value is delta H, which is put into this equation to find out the flow rate. But this equation will always overestimate the actual flow rate. If one measures the actual flow rate, for example, there is an opportunity to measuring the actual flow rate by collecting the fluid, then you will find that by utilizing this equation with the measured values of delta H from the manometer deflection, we will always overestimate this flow rate. The reason is such that this equation has been developed considering the fluid to be inviscid. So therefore, this pressure difference delta H manometer difference or the pressure difference is the pressure difference for the inviscid fluid. But the actual pressure difference which is registered in the manometer is more than that of an inviscid fluid. Now try to understand this physically. Why there is a pressure difference for an inviscid fluid? This is because of the difference in velocity. So velocity difference because there is a difference in area. So due to the change in area there is the difference in velocity or change in momentum. So due to this change in momentum or change in velocity there is a change in pressure. It is a mutual conversion between pressure energy to kinetic energy or kinetic energy to pressure energy, whatever you call. But that means, for example, here the kinetic energy is increased, so therefore the kinetic energy is increased at the expense of pressure energy. Pressure energy is decreased. So therefore the decrease in pressure energy, that is P1 minus P2, will depend upon the increase in kinetic energy. But for real fluid, over and above, there will be an additional pressure drop because of the fluid friction between the fluid and the solid surface. So therefore the pressure drop P1 minus P2 will be more. The P2 will be still lower than P1, not only because of increase in velocity but also because of the fluid friction loss. So therefore actual pressure drop in a real fluid in this situation is more than that what is estimated by an inviscid fluid. So therefore delta H is more than actually what it could have been for the use of this formula. This formula is determined by considering the fluid to be inviscid. So therefore Q is giving a higher value. So for that we write that Q actual, this is adjusted by multiplying this with a coefficient, that is known as coefficient of discharge. So coefficient of discharge is now very clear. So this is known as, that means if we calculate from this formula the flow rate, this gives you a higher flow rate. This is sometimes known as theoretical flow rate. That means flow rate which is calculated by considering the fluid to be inviscid but substituting the pressure drop from the real fluid measurement. So therefore this gives a higher flow rate. So this is multiplied by a coefficient of discharge CD, and this coefficient of discharge depends upon the flow rate, depends upon the area A1 and A2 of the venturimeter. That means venturimeter geometry and flow rate. But this dependency is very, very weak, and at a higher flow rate usually CD becomes constant, and it depends upon mainly the Reynolds number of flow, which I will tell you afterwards. You don't know this thing when you will start the viscous flow, Reynolds number. You will see that there is a number known as Reynolds number, dimensionless number characterizing the viscous flow, depends upon mainly the Reynolds number. But you must know at this stage at higher flow rate for all venturimeter and within all ranges of flow, CD is virtually constant and lies between a value of 0.95 to 0.98. That means it is very, very high. Usually it is made of brass. The venturimeter and surface is so polished that the friction between fluid surface and the solid is so low, so 0.95 to 0.98, this value of CD. Now the only job for measuring the fluid flow by a venturimeter is to calibrate the venturimeter. What is the calibration? Calibration means to know accurately the value of CD. How do you know the value of CD? I give you a venturimeter and tell you, okay, use the venturimeter. The venturimeter CD value is 0.99. You may doubt. Actually, the venturimeter which I have given so rough surface and so badly designed, its value of CD is 0.7. So there will be a tremendous discrepancy in the result if we use 0.9 as CD and 0.7. So what you do? You calibrate the venturimeter. What is meant by calibration? You find out the value of CD. That means you find the flow rate by any other measuring device which is more accurate than the venturimeter, which is usually a direct collection of flow. In case of an hydraulic circuit, then you measure the flow rate and you find out the value of CD with known values of A1, A2 and delta H. And you find out that in a range of flow rate, where you measure your flow rate, what is the value of CD. And then you establish a relationship between CD and flow rate, which is usually done for CD and Reynolds number. This relationship to establish is known as calibration of venturi meter, which is very important. That means to find out the exact or accurate value of CD, to use the venturi meter to find the flow rate from this equation. Alright, now let us see the next one is the orifice meter. Now when the venturi meter is well understood, orifice meter will not be a problem. Orifice meter is like this. A orifice meter is a orifice plate, that is a plate with a hole at concentric hole at the center. Now it consider a pipe. The orifice meter is like that. Let me draw a orifice meter with a orifice meter is like this, a little beveled side. So this is an orifice meter. So orifice meter, if you see, so this will be a circular plate. So this orifice meter with a concentric hole. So this is simply a circular plate which have a thickness which is very thin and a sharp edged orifice with little beveling like this, which is known as orifice meter. This is orifice meter. It is very simple in saying, you say plate, a circular plate, a thin circular plate with a concentric hole within it, a sharp edged concentric hole, which is known as orifice. So the sharp edged hole is known as orifice. So this is an orifice. So this is placed in a pipe. So this gives, when it is placed in the pipe where there is a flow and flow has to be measured, what happens? This gives an obstruction to the flow. So what happens is the fluid streamline behaves like this. And there is a vena contracta, as I have already told you. So these are the streamlines. These are the streamlines. So this is one streamline, center. So these are the streamlines. So what happens? Streamlines contracts because now there is an area contraction. That means this placing this orifice meter by flange, we place the orifice meter between the pipeline connections to pipeline connections. Then what happens? This provides a coaxial contraction to the path of the fluid. Then fluid streamlines of the fluid flow just contracts and then they form a vena contracta, that is the area, minimum cross-sectional area section which is very close to the orifice plate, that means fluids downstream. So this is the vena contracta. Vena contracta. Now what happens if we take a section here and if we take a section here, if this section is 1 and let this section is 2. Let us consider the area of the pipe is A1. Let us consider the area of the orifice in the orifice meter plate is A0. A0. Now this area, let us consider AC. AC is less than A0. This is a vena contract area. Now you see that V2 will be V2 or VC. This section 2, V is VC. VC is greater than V1 or less than V1? VC is greater than V1 because this is the maximum velocity with the minimum area, and P1 is greater than PC. PC is less than P1. So if we attach a manometer within this, then the manometric fluid will behave like this. So you take this as the delta H. Here also, now if you write the Bernoulli's equation between these 2 points, you can write that P1 by rho g. Again, if there is an elevation head at 1 and 2, P1 by rho g plus Z1 plus V1 square by 2g is equal to, if I write, now one tapping is made at this upstream portion where the fluid is almost uniform, fluid flow. That means usually this is made one diameter upstream. If D is the diameter of the pipe, one diameter upstream from the orifice plate. And usually this is made, this should be made theoretically at the vena contracta section, but it is very difficult to realize the vena contracta section. Usually it is made at D by 2 distance downstream from the orifice plate. It should not be far away from the orifice plate. In that case, a delta P, a high value of delta P is very difficult to be registered because fluid flow area is again expanding. So therefore the pressure is again increasing. You understand? So this part is the eddy portion. As you know, when the expansion is taking place, fluid is expanding, that is the diverging, streamlines are diverging, there are the flow reversal zones. So therefore you now recognize that this portion, if we can attach the manometer at the vena contracta section, we can get the maximum pressure drop. If we attach the manometer here, we will get a pressure drop which is equivalent to frictional pressure drop, because pressure drop due to momentum change we will not be able to capture. So therefore it should be at the vena contracta section. So down another connection, but it is difficult to realize where the vena contracta takes place. So it is usually made at d/2 distance downstream from the orifice plate. So let this section is 2. So these two sections better I replace as C section, because this is the contracted section, PC by rho g plus VC square by 2g, rather ZC if there is elevation net difference, ZC plus VC square by 2g, considering the fluid to be inviscid. Okay. So from this we can find out that V1 minus Vc, again the same thing is there. If you write V1 A1 is equal to Vc AC. Okay. So you just write in terms of Vc, then we can write it here that Vc square by 2g, V1 square by 2g, Vc, V1 is V1 A1, Vc AC by A1, that means Vc square by 2g. Similar way, 1 minus V1 is AC, AC square by A1 square, you follow it with the similar philosophy, is equal to 2g into P1 rho g, that means I write H1 star minus Hc star. What is this? This is the piezometric pressure rate at the section 1, this is the piezometric pressure rate at the section C. So that means Vc is equal to root over 2g H1 star minus Hc star divided by root over 1 minus AC square by A1 square. Alright. Now again H1 star minus Hc star, from this manometer equation, if rho m is the density of the manometric fluid, will be equal to root over, what is this? 2g H1 star 2g, the same thing, rho m by rho minus 1 into delta H. That means in terms of the deflection of the manometric fluid in the manometer, this will measure the H1 star minus Hc star. If there is if this is horizontal, so Z1 and Zc equal, so H1 minus H1 star minus Hc star, simply H1 minus Hc. That means, oh sorry, I am sorry, so these two. That means this is P1 by rho g minus Pc by rho g. It is as simple as that, divided by root over 1 minus AC square by A1 square. Now this is Vc. Alright. Now one step further, that again with the same logic, here itself I multiply with a coefficient. Why? Because if I substitute delta H from the practical measurements, that measurement for a real fluid, then this is more than what one can expect for an ideal fluid. So therefore Vc estimated is more, it is overestimated. So Vc is corrected with a coefficient. So this is known as coefficient of velocity. That means Cv into root over 2g rho m by rho minus 1, okay, into delta H root over 1 minus AC square by A1 square. So this is the velocity, expression of the velocity. So now if we find out Q is equal to, now this area, now you see Vc is this area, that is the AC, that is the area of contraction, that is Q is equal to AC into Cv into root over 2g rho m by rho minus 1 into delta H divided by root over 1 minus AC square by A1 square. Alright. Now AC we can replace as, what is AC? Cc into A0, because we define the coefficient of contraction at AC by A0. That means, as you know earlier also, we define a coefficient of contraction, that is the ratio of the area at the vena contracta to the geometrical area of the orifice or the aperture. So this is AC by A0. So this can be written as, all now I express in terms of the geometrical area which we can measure. We cannot measure AC, but we know the orifice plate diameter, that means diameter of the orifice in the orifice plate. So CC A0 times CV into root over 2G rho m by rho minus 1 delta H into root over 1 minus AC is CC square A0 square by A1 square. So this is the simple equation. Alright, then CC into CV we replace as CD. So we define CD as CC into CV. CD is the coefficient of discharge. CD is equal to coefficient of discharge. Discharge. So if I write this as CD, then we can write this. I can write, now you see this, CQ is equal to CD A0 into root over 2G rho m root over 2G rho m by rho minus 1 divided by root over 1 minus CC square A0 square by A1 square. Rather, this part I take out into root over rho m by rho minus 1 into delta H. Alright. Now this part is fixed. For a orifice meter, if I know its value of CD, if I know the value of A0, that is the orifice diameter of the orifice meter, the diameter of the central hole of the orifice meter, 2G 1 minus CC, if I know the value of CC for this orifice meter, A0, A1, if we know, this can be written as a constant, all these things, times this one. This one is varying depending upon the manometer. That means depending upon the manometric fluid, the rho m value will depend upon the manometric fluid used and the deflection of delta H. That means this C is known as constant of the meter, constant of orifice meter, which is a function of the geometry of the orifice meter, and its value CDCC, which is again a function of A0, A1 and the flow rate. A0, A1 and the flow rate, that means diameter of the orifice meter, diameter of the orifice meter, hole, that means diameter of the orifice in the orifice meter, diameter of the, that means the area of the pipe in which the fluid is flowing, and the values of CDCC. So this is a purely constant for a given orifice meter, for a given pipe diameter and in a given range of flow. Usually at a higher range of flow, it is independent of the flow rate. So if I know the value of C, that means the constant of the meter, then I can find out. So now in using an orifice meter, the main or the pivotal job is to find out accurately the value of C at different flow rate. So that if I use the orifice meter, I can immediately find this value from my manometer. If I know the manometric fluid, I can find out rho m. But when I will find out Q from here, I must know the value. If the orifice meter constant is given, I do not bother with all these equations, root over 2G by root over 1 minus CC square, I simply multiply. But what I must know very accurately the value of C. And to know very accurately the value of C is, or to establish an accurate value of C within a range of flow is known as calibration of orifice meter. So this is very important, a calibration of orifice meter before it used. So usually the value of C for orifice meter, actually this value of CD for orifice meter varies between, rather we can write the value of C considering these things, A0, A1 usually in the range varies from 0.75 to, 0.65, 0.60, to 0.65, 0.60 to 0.65. This is the value of CD for the orifice meter. Alright, now we come to flow nozzle. Well, now we come to flow nozzle. Flow nozzle is an intermediate thing between these two. Now, flow nozzle is like that, it is like a nozzle. That means in the pipeline, you just provide a nozzle like this. You just provide a nozzle like this. That means if you see the sectional view, it will be like this. a nozzle. A nozzle is attached to the flow. That means what happens? It is unlike the orifice meter, there is a converging part. So streamlines are smoothly converging. But what happens, unlike the venturi meter also, this part is not a diverging one. So it cannot smoothly divert. So streamlines goes like this. So streamline goes like this. That means this is the streamline pattern, and there will be eddy formations, more eddy formation, more losses will be there. So this is a flow nozzle. So if we make a connection just at the downstream of the nozzle and somewhere here in the upstream, we get a pressure drop delta P. Let this section is 1, this section is 2. So delta P is P1 minus P2. If this is registered by a manometer, same thing delta H, we can find out the flow as a function of delta H. It's same philosophy. But here you see the flow nozzle, the losses are more for the venturimeter. Why? Because this part there is no in this section there is no divergent part. So fluid stream after converging smoothly along the surface, they diverge like this, so that the formation of eddies takes place due to separation losses. So therefore in this case the total energy loss in case of this, that means if you have a total energy here, that total energy loss will be more. But this is counterweight by its lower cost. Whereas in case of a venturimeter, if you recollect, in case of a venturimeter, if you go like this, the energy loss from a upstream section to downstream section is very low, because usually the separation loss is minimized and this angle is very small, so only frictional losses predominates, and that too the surface is so polished, so the friction loss is very small. Nevertheless there will be losses, but H2 is very less than, the difference between H2 minus H1 is very small, so energy loss is very small. Whereas in case of an orifice meter, the energy loss is tremendous, because it abruptly contracts and makes the vena contracta and then again it diverges. So the energy loss, that H2, H1 and H2 is maximum in case of a orifice meter, but it is the cheapest. So it is the costliest, it is the cheapest. Energy loss is minimum, energy loss is maximum, and this falls in between the two. That means if we compare the instrument, you see the meters, then you cause the accuracy, and then you tell the cost, then you tell the loss of total energy, and then the value of CD. Then first you write the venturimeter. Venturimeter accuracy is maximum. Cost is also not maximum, you write high. Cost is also high. To make a venturimeter, and the length is very high in the divergent part, made of brass, so therefore cost is very high, loss of energy is very low, and CD value 0.95 to 0.98. Similarly, orifice meter is other extreme. Accuracy is very low, cost is also low. So these two are compatible. So loss of energy is very high, and this value is 0.65 to 0.6. And flow nozzle, or simply nozzle, flow nozzle, this is intermediate between these two. Intermediate between these two. That means I can write intermediate. All these three columns, intermediate between venturimeter and orifice meter. And venturimeter and orifice meter. I am sorry for the handwriting is bad. And the value of this also CD lies between 0.75 to 0.80. All right. Okay. Thank you for today.